An element is a pure substance. We cannot subdivide it, well, samples of it, further and get different properties. No, I'm not talking about cheating like, say, molten sodium versus solid sodium. Well, of course they have different properties. You can hit somebody over the head with a bar of solid sodium, in theory. Don't actually try it though, because sodium reacts pretty badly when in contact with water, and it oxidizes very rapidly in air. So sodium bars actually have to be stored under oil. So how about we try a slightly less dangerous substance? Okay, molten iron obviously has some very different properties from solid iron, which you can whack people or animals or whatever with if you like. Try not to though, unless strictly necessary, i.e. in defense of self. Alright, or others. Okay, elements, well, they all have the same type of atom. And how do we identify atoms? Well, atoms are identified by their proton counts. So say you have 6 protons in an atom. It's carbon, period. Like, no matter how many neutrons you have, if it has 6 protons, it's carbon. And it will behave like carbon because, chemically behave like carbon because, well, we aren't doing physics right now, so no, you can't pack so many neutrons around it that it's, well, pretty much neutronium, i.e. Neutron star material, but so degenerate matter. So for chemistry, we're dealing with really, out of these subatomic particles, we only care about electrons, protons, and neutrons, and even then, really, we only care about electron interactions. The nuclei barely matter other than what we can use them for in biology class. In physics, yeah, you do a lot with the nuclei, but even in chemistry class, you barely deal with the nuclei. It's all about how the electrons interact with each other, or the distributions of the electrons interact. So electrons are negatively charged, they move around freely, and they are about 1 in 1823 AMU. AMU is short for atomic mass unit. Mass unit. And it's used interchangeably with Dalton. Dalton is named for John Dalton, one of the scientists who participated in figuring out the structure of atoms. Now, 1 Dalton is about the mass of a proton or neutron. Electrons, we basically deal with them as if they don't exist for our purposes. Now, yes, if you have a particularly massive atom, perhaps you should pay attention to the decimals places, like say the 100th place. Like say uranium, which has 92 protons and 92 electrons when it's uncharged. The protons and electrons are equal in number when the atom is not charged. When the atom is charged, though, you can remove electrons or add electrons, but the protons and neutrons stay put. This is a simplified diagram of a fluorine atom. As you can see, the first electron orbital is also the entirety of the first electron shell, and it can only fit 2 electrons. This shell only has 1 orbital in it. The second electron shell has 4 orbitals in it. Here we can see 1s2, 2s2, 2p5. This is how we would write the electron configuration. The s orbitals, s can go up to 2, p can go up to 6. D can go up to 10, and F can go up to 14. We will discuss this in greater detail shortly. But the atomic number is the number of protons. It also is the element number if you look at the periodic table. It's a subscript to the left of the element symbol. What's a subscript? Well, a subscript is, this is fluorine, it's element 9. Subscript is below the normal text and it's smaller, so it's 9. It's the left. And the mass number is a superscript to the left of the symbol, and it gives some of the proton and neutron numbers. This gives you the mass in Daltons or AMU. So in this case, it's 19 because there are 9 protons and 10 neutrons. This happens to be the only stable isotope of fluorine. However, many other substances have multiple stable isotopes, such as, say, carbon, which is element 6, can be 12 or 13, and these are stable. Carbon 14, however, is not stable. It decays to nitrogen 14 over time. We usually take the atomic mass as equal to the mass number, but if you're doing chemistry class, you will have seen that consulting a periodic table is better. For example, sodium has an average atomic mass of 22.99 on Earth. Carbon has 12.01. How could this be? I mean, we define atomic mass unit as, well, 1 mole of carbon-12 has Avogadro's number of atoms, and it has a mass of 12 grams. So how could it be that on Earth 1 mole of carbon is 12.01 grams? Well, that's because there's enough carbon-13 for the weighted average to be pulled up. There's going to be some carbon-13 mixed in there on average, and it'll average out to 12.01 grams per mole. Also, 12.01 AMU. The atomic mass unit multiplied by Avogadro's number, which is about 6.022 times 10 to the 23rd. That multiplied by the AMU is about equal to a gram. And I say about equal because this is an approximation. Isotopes, well, they vary in neutron count, as we saw earlier with carbon-12 and carbon-13, which both have 6 protons, but carbon-12 has 6 neutrons, carbon-13 has 7. Isotopes vary in neutron count, and therefore they vary in mass. Now, if the isotope is unstable because it has too many neutrons, or perhaps too few neutrons, or it has an unstable nuclear configuration, then these will decay. They will give off energy and or particles. Now, say you have a very, very heavy isotope, and you need to get the atomic mass down for it to be more stable. Well, then usually you would throw off alpha radiation, which is 2 protons and 2 neutrons. What is this? Well, this is just helium 2+. So it's just a helium nucleus. 2+ because it has a positive 2 charge with no electrons to neutralize it. So alpha radiation. Beta can be beta positive or beta negative. And beta negative is just an electron. Beta positive is a positron or anti-electron. Another form of decay is electron capture. So one of the electrons that's orbiting the atom just spirals inward and hits a proton. And you end up with a neutron. So this is one way to deal with too many protons and not enough neutrons. Now, beta positive decay can be a way to deal with the same thing. Different methods of decay may apply to the same atom with different frequencies and reaction constants. If you have too many neutrons, you can throw off an electron, and because of conservation of charge, you just ejected a negative from the nucleus. Therefore, one of the neutrons must become positively charged. So it's now a proton. We also call radioactive isotopes radionuclides, or just radioisotopes, because, well, it's related to the nucleus, therefore nuclide. Yes, you can technically get the atoms to throw off energy without messing with the nucleus by, say, energizing some electrons. But that tends to release the energy much faster. And how do they discover radioactivity? Oh, they put a chunk of uranium in a drawer with some photographic film, and it turned out that it left an exposure on the film. Well, it must be giving something off. Yeah, well, that and a few other incidents came about, and radionuclides, radioisotopes, isotopes were discovered rather later, after radioactivity, like long after. So radioactivity, well, you have to not be actively messing with it. At least you have to leave it alone for quite a while, and it has to still give off these energy waves or particles or whatever it's doing. They didn't know at the time. It's on its own. Now, of course, there are a few flavors of what it could be doing. Alpha particles, because they're just helium nuclei, they cannot penetrate a good piece of paper. They don't get very far in air, and they do not penetrate skin. Electrons or positrons, depending on the level of energy they have, sometimes the positrons or electrons don't travel well through air, but for the most part they can be blocked safely by just a sheet of aluminum. On the other hand, if you're dealing with gamma rays, which are the result of a high energy nuclear configuration dropping to a lower energy one, so settling to be more stable and releasing energy, or alternatively it's emitted with an alpha or beta particle being thrown off, or with an electron capture event, gamma rays are pretty dangerous. Now, yes, okay, it could be actually lower frequency, but we use gamma just to designate photons in general that are thrown off during these reactions, even if they're not actually considered gamma rays by frequency. Well, this isn't physics or chemistry class, so we should hurry up. Okay, how do we apply this stuff to biology? Well, if we want to see whether, say, DNA synthesis is happening in these organisms, we can add a radioisotope and track how the nucleotides that are tagged with the radioisotope are uptaken by the organisms and, say, incorporated into their DNA. And we can compare the amount incorporated under different growth conditions, such as temperature, acidity, whatever. What else could we do? Well, we could use it for diagnostics. Strontium is very commonly used to diagnose bone cancers. Positron emission tomography in general is used for, well, a lot of different types of clinical oncology. This equipment here, this thing detects gamma rays that come from positrons being thrown off into the patient's body by the radioisotope and annihilating with electrons inside the patient. In other words, by taking in those radioisotopes, we are allowing them to dispense antimatter inside us so that we can figure out what's wrong. Now, given the average person's record in dealing with things that can have some unsafe or interesting side effects, or are described to have interesting side effects, telling them that this is a way to dispense antimatter inside yourself is perhaps not the most brilliant of ideas. Let's not advertise it like that. Okay. This particular scan image used fluorine 18 fluorodeoxyglucose, FDG. This is known as FDG PET, which is a common technique in oncology. You can see the bladder. In bladder, where metabolized FDG has accumulated. You can also see something is a little bit off here. Now, here's a kidney. Well, okay, that's very roughly outlined. There, better. Here's another kidney, roughly. And there appears to be a bit of a problem here. Now, yes, you can also see the brain, because the brain uses a whole lot of glucose. The brain consumes an enormous amount of nutrients relative to its size. However, it has proven advantageous over time for humans to have larger brains, allowing more complex neural interactions, therefore more intelligence, at least in theory. There are a lot of very brilliant people with proportionately smaller than average brains, and there are also a lot of not so intelligent people with larger than usual brains. So the correlation is not firm, but compared to the rest of the animal kingdom, well, yeah, a larger brain is rather important to forming sufficiently complex thoughts for sapiens. Curiously, I'm most used to FDG in the form of Frederick der Grosse. Sorry for any mauling of the name. We English speakers know him as Frederick the Great. Okay, anyway, energy levels of electrons. Now, the nucleus is not anything like this. Like, if you look at an atom, this is not anything close to what it looks like. If you have an atom be a sports stadium, yes, okay, that's a very slack comparison given that we know sports stadiums can be pretty small, so just, I don't know, 20 meters wider than the field on all sides, so a 20-meter rim around the field, or they can be absurdly huge. Yeah, that's a pretty loose comparison, but your nucleus is going to be somewhere between this end of this thing and this end of this thing in size. So something comparable to your pinky fingernail. So that's a pretty small nucleus compared to the size of the atom. As for the electrons, well, they are much, much smaller, and there's anywhere between gnats, so just those tiny little insects you see flying around, that you can't even hear buzz when they come near you. Oh wait, that makes it sound scary. Okay, or ants. Okay, so ants, yeah, I'm talking about pretty small ants here, not those huge things that sometimes you see wandering around. Perhaps I should have rethought this a little. Okay. Bad jokes aside, and sarcasm aside, nuclei do not really interact in chemistry. If we're ramming nuclei together and expecting them to do something, we're already going into physics, i.e. nuclear fusion or fission. Chemistry, we're mainly having the nuclei approach each other, and then the electrons interact, or they just bounce off each other if they're not correctly aligned to interact. And for biology, since it's applied chemistry and we don't pay much attention to nuclear physics, well, you can get where this is going. We don't care too much about the nuclei. It's mostly going to be about the electrons. Well, okay, sure, because the nuclei can decay, such as from carbon-14 to nitrogen-14. That also affects the electron configurations and charges of the atom as a whole. So yeah, that is relevant. Why else is it relevant? Besides those sudden changes. Well, there's also stuff like carbon dating. But generally, we're dealing with electrons. So electrons vary in energy level, and energy level is defined as the ability to do work, i.e. cause changes. For example, if I hold a brick up here, it is capable of probably killing a small animal or breaking my foot if I drop it. If I hold the brick directly touching my foot, well, and then let go of it, no, it's not going to break my foot. So, an electron that can drop to a lower energy level will eventually do so and release potential energy in the form of light or heat as it does so. Yes, there is some reaction coefficient involved. That sort of stuff. Reaction rates we don't pay that much attention to in biology. Although it is important, that's why we are as warm as we are. Being warmer allows reactions to occur faster. Now, potential energy is energy that's possessed by matter due to location or structure. For example, if I have an elastic band and I pull back on it, well, first of all, I doubt most elastic bands you can get normally can actually go this far. Okay, if I pull back on an elastic band and then I let go, well, that elastic potential energy will convert to kinetic energy, and if I do it right, it'll keep on flying. There's also gravitational potential energy, there's electric potential energy, and so on. Now, given that the nucleus is positively charged and the electrons are negatively charged, and we know that opposite charges attract, or at least we hopefully know this, then, well, that is potential energy. The electron will tend to fall closer to the nucleus. Of course, usually the electrons stop short of the nucleus, unless we're dealing with electron captures. And they end up in the lowest energy level that they can be in. Now, it could be there are already other electrons, in which case, say we add a 10th electron, it would have to go here. Now, that's the second electron shell. Electron shells each have a characteristic average distance from the nucleus and therefore characteristic energy level. The energy levels are quantized. That means it's like stairs. You can't stop halfway in between. At least the electron cannot stop halfway in between. It has to either go the whole way up when it absorbs some light, or go the whole way down when it emits some light. Now, how many steps it goes down? That may vary. So you have different emission bands for one atom for an electron going down different amounts from either from different energy levels or to different energy levels. For biology class, we'll tend to represent energy levels and electron shells by concentric circles. This was the way they thought way back in the late 19th century when they first figured out that electrons circle the nucleus. However, in reality, no, electrons don't actually do this. First of all, electrons move in 3 dimensions. That's one big thing. Second, it turned out that the concentric circles, they had a puzzling pattern. Biology is most focused on the first 20 elements, so we end at here when we have electrons in a 2 first energy level, period, 1, 2, 3, 4, 5, 6, 7. So, first we have 2 electrons in the first electron shell, then we have 8 in the second, and then 8 in the third. And suddenly, when we get to the 4th shell, we notice that we end up filling out a huge number of additional electrons before we get from calcium to gallium. This lot is actually part of the 3rd shell. How could this be? Well, that's because the orbitals go in, as I mentioned earlier, and then, well, the 3D orbitals are actually so crowded that 4s2 is actually lower in energy. You can think of it like this. This is the order in which they fill up. And 4 is the first one where you show up with 4f14. Of course, there's also 4p6, 4d10. So in other words, this block and this block, which are known as the representative elements, these are the p orbitals, and these are the s orbitals. Hydrogen and helium are slightly special because there's only one s2 for the first electron shell. This middle block is for the d orbitals, and the lanthanides and the actinides down here are f. So the transition metals are for the d orbitals. Since the d orbitals are not actually exposed because, well, the 4s2 is on the surface, they are on average further from the nucleus. Since the 3d orbitals are not so exposed, these transition metals, the s orbitals, control a large part of their chemical interactions, so they tend to lose electrons, rather similar to the alkali and alkaline earth metals. Now, these specific details, either you've covered them in chemistry class before in lower grades, or you really should do that. We won't go too far into that. But if you have 8 electrons in your valence shell, that's considered a stable octet. If you have, say, hydrogen or helium or lithium or beryllium, so the first few, these, and boron sometimes, tend to go to a helium electron configuration, which means, of course, that's still a filled outer shell, but it's only 2 electrons. Now, if instead of losing electrons to become stable, you have to gain electrons to be stable, well, we can do this by sharing, and that's how molecular or covalent compounds are formed. Ionic compounds, on the other hand, achieve stable valence shells by transferring electrons. We usually draw electron orbitals as circles, but yeah, no, they're actually a lot more complicated. So the 1s orbital is this circle you see in the middle here that's smaller than the 2s orbital, which is also round. It's a sphere. So in 3 dimensions, it's spherical, so a ball. These 2p orbitals, they are lobed, kind of like an infinity symbol, or an 8 laid on its side. They are sometimes described as dumbbell-shaped. Now these are probability distributions. Each orbital is only the volume that encloses 95% of the probability distribution. The electron can actually be anywhere in theory. Remember, a probability distribution actually tells you nothing about the instantaneous behavior. I mean, telling me that, if I roll 2 dice, 7 is the most likely sum. Well, does that tell me anything about what the outcome of the 2 dice actually is? I mean, for all I know, the 2 dice could, in theory, shatter and show every single dot facing up. Well, how many did I just roll? So, we are not going to get too far into the probability distributions. Just know that the orbitals are probability distributions. They are where the electron is most likely to be found. They are mathematically defined volumes of space. And that not more than 2 electrons may occupy a single orbital. And even then, they have to have opposite spin. Electrons spin as they move. And we write them as, say, this, if they are in the same orbital. But that's something we can say for chemistry class. Now, atoms will react to complete their valence shells, and when they do, it's almost always the unpaired electrons that are involved. Coordinate bonding, like protonation of water or protonation of ammonia, well, no, that's different. That actually uses a lone pair and donates both electrons given by this double-ended arrow, as opposed to the usual bond, which is, say, bromine to bromine, single-sided arrow, and that gives us Br. This is a Lewis diagram with the dots for electrons. So, for water to coordinate bond with H+, so a proton, we have both electrons coming from the oxygen, and this leads us to OH, H, H, and 2 dots. And what else? Conservation of charge, guys. And besides, there are only 5 electrons nominally belonging to the water compared to its usual complement of 6. Whereas each hydrogen has 1 if these bonds were not polar, and that is normal for them. These bonds are actually polar, so the electrons spend most of their time near the oxygen, which has high electronegativity compared to the hydrogens. It tends to pull electrons toward it. But, well, in this case, we still designate the oxygen as positive because, well, assuming these were evenly split, it has less than it usually would. Now, some problems. How many neutrons does helium-3 have? How can H3, so tritium, hydrogen 3, decay to helium 3? Helium 3 and tritium are considered the prime materials for fusion reactors, or attempts at fusion reactors. Deuterium is also used, which is H2, hydrogen with 1 neutron instead of 2 as per H3. Helium has 2 protons, so has 1 neutron. And H3 can give off something to become He3. What could it possibly be? Well, the mass is conserved and the charge is conserved. Now these atomic numbers, they give you the charge in the nucleus, which means that we're looking at an electron with, well, -1 charge and 0 atomic mass units worth of mass. That's an approximation, but it's good enough. You also have some energy being given off because tritium is unstable. So this is beta negative decay. You can also write this as beta negative if you like. Now let's write the chemical symbol with superscript and subscript of a carbon atom. Carbon, we know, is element number 6. You should remember the first 20 elements. The rest, well, actually, there are a few that you should still remember, such as, say, selenium, which is used in selenocysteine to replace sulfur. Selenocysteine is a rather rare amino acid that's sometimes used in humans and other organisms. It's not actually listed generally as an amino acid that's commonly found in us, but it's used nonetheless. So, write the chemical symbol of a carbon atom, well, 6, with 8 neutrons. Well, 6 plus 8 is 14. This is carbon 14. Its decay half-life is about 57-30 years. This allows us to use it for most archaeological purposes within historical time and recent prehistory. In the past, people working out how old a fossil was only really had the rock layers that were above and below it to go off of. In other words, they only had relative dating. Now, yes, relative dating, you can do a lot of calculations for, say, sediment deposition rates, but that's still very, very inaccurate compared to, in more recent times, use of radioisotope dating. Now, we use radioisotopes with a lot longer half-lives than carbon-14 for that. In fact, some of them have such long half-lives, like uranium-238, that they are usually dealt with as if they are stable. Holding a brick of uranium-238, refined uranium-238, in your hand for a while, so, like, not for years at a time, for a while is going to give you less actual radiation than, well, taking an airliner flight. Now, which orbitals are occupied in a chlorine atom? Well, we consult our periodic table if need be. This, first, we know that 1s2, so the 1s orbitals are fully occupied. Chlorine is in the 3rd period. 2s2 is also occupied. 2p6 is also occupied. 3s2. And then how many on 3p orbitals? Well, we have 3 of them, so 3 orbitals that are of the p type for each energy level. And in this case, we can count them and find out that there are 5 electrons in these. The maximum capacity is 6 electrons in the p orbitals of a particular energy level. Remember, guys, each orbital can hold 2 electrons of opposite spin. Now, what common properties exist across periods or down groups in the periodic table? Well, across a period, the outermost electrons are going to be labeled as being at the same energy level, but we know that, say, 4s2, 3d10, 4p6, yeah, they aren't that close in energy level. So across a period, very little. Very few properties. Smaller atoms on the right because compared to expanding to a whole new energy level, having more and more protons in the center, compacting the outer electrons inward by pulling on them harder, that just kind of makes intuitive sense, I would hope, like to those of us familiar with attraction of opposite charges. So smaller atoms on the right, and also usually high, and usually more electronegative too. Electronegative, i.e. less likely to lose their electrons. And when in a covalent bond, more likely to pull the electrons towards them. Okay. Down groups, however, similar chemical reactivity. Properties. This is because, well, it's most obvious in the alkali metals, first group, the alkaline earth metals, second group, and in 17th group, i.e. the halogens, and 18th group, the noble gases, but they will tend to go for the same configuration, i.e. either -1 or +2 or +1, or just does nothing for their stable octet. The other representative elements, however, as you go further and further down the group, you eventually run into the metalloids, which have some metal-like properties and some non-metallic properties. And in the case of, say, SN, which is tin, that behaves very, very differently to carbon. Carbon, silicon already behaves noticeably differently from carbon. So groups have similar chemical properties, but the physical properties can differ a lot. Similar chemical properties if of same metallicity or lack thereof. Because I can assure you that a brick of tin is slightly less combustible than a brick of carbon in an oxygen atmosphere, at least. These two blocks are known as the representative elements because, well, the transition metals have a lot of properties in common because their valence shell is mostly going to be just S2. Yes, there are a few that are S1 or even S0, but, well, if you have similar valence shells, you're going to have similar chemical properties. Yes, okay, there's the metalloids and then metals transition, but that's another story. Okay, well, where are the largest atoms on the periodic table? Well, as we go down, we add more electron shells, so more layers, like an onion. And we know that as we add more protons, as we go across a period, the layers smoosh together more. Therefore, the largest atoms are found down in this corner. Francium. And, well, maybe whatever's found that goes under francium. But the chemical properties of a lot of the substances in the last row, they are a little bit difficult because they have very short half-lives. Well, that's it for this section. That's it for now for electron shells and orbitals. You can discuss this more in chemistry class, or physics for that matter, but we will now proceed on to the next section. See you then.